The next talk, the third talk will be given by Professor V. Balaji. He is currently a professor in Chennai Mathematical Institute. He works in the area of algebraic geometry and representation theory. He has several awards and recognitions to his credit. He is recipient of the Santeshwaru Bhatnagar Prize, the Desi Bose Fellowship. He is also a fellow of the Indian Academy of Science, Indian National Science Academy, National Science Academy. He has also a very long-standing association with IMSC, starting from when he was a student here. He will talk to us on deformation and degeneration in algebraic geometry. Over to you.
Thank you very much. It's a pleasure to come back to math science and give a talk. I belong to the first new generation of math science. We are from 62 to 84. It was one type of math science, and then there was a sudden change in 1984 when Seshadri and Sudarshan and others came. I joined math science in 1984 in November. I moved over from ISI Delhi. I had a short stint there. And in fact, I'm 2-3 months senior to Balu in math science. And a few of us came. This was the first batch of students in the new math science regime. And myself with Seshadri, Sukumar Adhikari with Balu. We had Anand Antony who worked with Krishna Madali. And there was another fourth student whose name was Salai Davakudi, who was working with Aladi Krishnaswamy. And so it was quite an exciting period then. 5 years of a lot of drama, high level of mathematics. We had a range of top class visitors in math science in those days. Seshadri was instrumental in getting some top class people to inspire all of us. And of course, we had exciting times, a lot of secret talks, dramatic, mysterious happenings, shaking of the foundation of the institute, new things getting created, old things going out. So it was quite a great time to be here. And I moved over to CMI along with Seshadri in 1989. So my 5 years stint in math science is etched in my memory because that was my formative time with Seshadri. Okay, so today I'm going to give a pure math talk. I brought my special Hogoromo chalk as a tribute to algebraic geometers who use this. So as I said, I'll speak about a general theme, deformations, and degenerations. Both these played a very important role in the development of algebraic geometry in the post-1950s. They were taken up in very serious ways. They have played a serious role in what is called the moduli problems in general. So we are looking at problems which involve what I call classification. So we are looking at a hypothetical space which is supposed to parameterize, I'll say, a class of objects, algebrogeometric, or analytic, complex analytic objects. We are interested in parameterizing them. Say, for example, we could look at algebraic curves, or complex analytically, we can think of Riemann surfaces, or we could look at algebraic surfaces. These are dimension 2 objects. This is dimension 1 objects. This is dimension 2, or more generally, other high dimensional geometric objects. What is the broad theme? We fix the so-called topological type of these geometric objects. For example, if you work with curves or Riemann surfaces, we should think of them topologically as a sphere with several handles attached. So these handles will be the so-called genus of the Riemann surface. So topologically, they will all look like this. But what we want to vary is what is called the complex structure. And this problem was already studied by Riemann way back in the 1850s. So this classification question of curves of a fixed genus where you fix the topological type and allow the complex structure to vary is one of the basic examples of a moduli problem, where we fix this kind of some sort of invariance, topological invariance, and then allow the natural underlying structure to vary, which is the complex structure in this case. So we could also look at, instead of these, we could also look at other objects which have been closer to my work, which is sheaves or bundles on a fixed object. So for example, you fix a Riemann surface, which means you look at a sphere with so many handles attached and give it a complex structure. You call it X, just abstractly draw it like this, and we can look at geometric objects which lie over this. For example, we could look at the tangent bundle of a Riemann surface. We could look at other natural algebra geometric constructions. We fix what is called the rank and the so-called Chern classes. Again, the topological data we fix, and we allow the holomorphic structure to vary. And these objects were studied, for example, by Jacobi. It's called the Jacobian of the so-called Riemann surface. We fix line bundles or rank 1 vector bundles, which are natural constructs on these Riemann surfaces. We fix their Chern class or degree, as it's called, and then look at how the holomorphic structure varies in them, and that gets a nice algebra geometric structure. So this is yet another solution of what is called a moduli problem. Okay, so what is the theme of deformations here? So let me be a little more formal here and just define what do I mean by a family of objects. So what do I mean by this? So I say that, I look at a picture of this kind. This is in whichever category I work in. Assume that we are working in algebraic geometry category. It's a certain class of where polynomial solutions are always being used here, as our topology is what is called the Zariski topology. And so my objects are algebra geometric objects, and I look at morphisms between them. Morphisms in every category, the morphisms carry the properties of that category. So this is an algebra geometric morphism. And what we want when we talk about a moduli problem is that we want the inverse image for each point here to lie in our class that we wish to study. So that's what is called a family of objects characterizing a moduli problem. And these morphisms are supposed to have some technical properties which are usually something like properness and flatness. These are technical terms which essentially encode the property that you don't want, for example, the topological type to change or the topological invariance to change and similar things. So that's the kind of objects we can look at. Or we can also look at, this is for this kind of objects here. For the second kind, I fix one object. So I look at the Riemann surface X. I look at a parameter space S. And I look at this projection map X cos S to S. I'm looking at family of sheaves, a family of objects on X parameterized by S. So this is, you are expected to have some properties called flatness over S and invariance, which are what are called Hilbert polynomials, to be constant. So we are studying sheaves which are on X parameterized by spaces like S. That's the second kind of moduli problem that I'm talking about here. In either of these cases, it's a rather difficult question to parameterize these things, and this difficulty was seen early in the 50s. And what was a beautiful contribution, a rather deep contribution of Codera and Spencer. Codera incidentally got the Fields Medal in 1954 for several of his deep contributions, along with J.P. Sayre. And so Codera-Spencer theory says that if I'm interested in studying a moduli problem, I'm interested in such families of objects. To understand a particular object in this family, one would like to know the local properties of this so-called moduli space. And these local properties of this moduli space can be understood even before we have a notion of the full space of the moduli problem. So this is the kind of philosophical thought that you may not, you may be interested in classifying certain objects, which is what is usually called functorial, a functorial description of the objects that we wish to classify. But we can, in some sense, understand local properties of what we wish to have even before we have the entire space. And this notion is what I call understanding the deformations of an object. So let me just quickly say what I mean by that, and a little formally here. So let's look at something like family of Riemann surfaces. So let's look at X to S, where each pi inverse S, I also fix a base point S naught here. So I'm looking at a marked space S comma S naught, and I'm looking at a morphism here, which is fiber-wise Riemann surfaces. And these all belong are Riemann surfaces. And just as in all geometric constructions, be it in differential geometry or algebraic geometry, what we ask is, a deformation is such a family where, I say that I look at this and look at the inverse image of the base point S naught, then such a family X, which has some nice properties. For example, this is what I'll call it's a smooth morphism, which has those properties of flatness. And so smoothness would also say that the differential structure doesn't change in this family. So I look at this picture here. So my picture should be something like this. And I have a base S, which we could assume is a one parameter base. So I have a Riemann surface in the center. A deformation is constructing such a family of objects over S. This is a very general definition. And so the families that we are looking at, a moduli problem, in some sense parameterizes some sort of an optimal family of deformations of given objects that we are looking at there. But what we wish to look at is a local property of an object. So suppose I fix this point S naught, and I want this to be isomorphic to X in my category as Riemann surfaces, for example. Then to understand the local property, what Coderre and Spencer spoke about as deformations, as what I call first order deformations of these objects, is instead of understanding the total space here, I wish to understand the tangent space to this proposed moduli space M at the given point X. So can I speak about the tangent space or expected tangent space for a good moduli problem even before I know the full solution? So what they did was, so they look at something like a trivial deformation. So this, if I look at just the second projection here, all objects are isomorphic to X. So this is what is called a trivial deformation. And we wish to classify what may be called locally trivial deformations. Just like vector bundles are locally trivial objects, or principal bundles are locally trivial objects. So you look at a trivial deformation of your object X, and then look at locally trivial deformations. So I look at, so question is classify locally trivial deformations. And as one would have it, this is like in usual vector bundle theory. A vector bundle is locally, which looks like a product of the base cross a given vector space, say complex vector space Cn. So all patching is done. We are looking at local automorphism groups of objects. And similarly for, if you fix this trivial deformation, we have to consider local automorphism groups which allow us to do patchings. So two local deformations are said to be are patchable if you can identify the local automorphism groups of those objects. And then your deformation, total deformation, is classified in terms of what may be called sheaves, which co-cycle elements which take values in this so-called local automorphism groups. So what was proved by Coderre and Spencer was that if you wish to understand the local deformation space, then there is a very natural cohomological space which is very easy to write down and compute associated to the given space X. Tx is the tangent sheaf for that, and all your deformations locally are classified by elements which come from this first cohomology group. And this led to understanding moduli problems in rather deep ways, and several developments took place. And this is, in some sense, let me say as a summary, that deformation space gives you a first order picture of a larger geometrical classification problem, and that's what is deformation theory all about. Okay. So the second theme that I wanted to talk about was degenerations. This is the other end. So you start with some smooth object. I mean, you already have some sort of a classifying picture, for example. So let me give this standard example. So this is Riemann's modelized space of Riemann surfaces of a given topological type. So that's a nice space which Riemann studied. And then one could compactify the space in some nice way, and this is called so-called Deligne-Mumford compactification. Okay, so they even proved that this space is nice and connected. So this space has already been constructed as a moduli problem. I mean, there are several solutions to this kind of question. Modern mathematics looks at solutions to these problems from the standpoint of stacks, which means basically looking at deformation theory and trying to glue up the local deformation spaces and trying to construct a geometric object. Or we could look at putting all the objects of a given type in a big space and trying to see whether there's a natural equivalence and do what is called geometric invariant theory as studied by Mumford. So there are two ways of constructing these moduli spaces, at least popular ways of doing them. So in this case, I look at the Riemann moduli space and compactify that in the Deligne-Mumford sense. So there's a large open subset which looks like Mg here. This consists of your smooth Riemann surfaces of genus G. And at the boundary, Deligne-Mumford attach some equivalence classes of what are called stable curves, which are singular, but which still are what are called arithmetic genus G. And so this space, this total space, is what is called Mg bar here. And when I talk about a degeneration, I'm in some sense trying to construct a path from a smooth object to a singular object in this total space. So that's a degeneration, a smooth object degenerating to a singular object, a smooth object degenerating to a nodal object. So you could look at this principle, and a natural question to ask is, can one have a better understanding? This is just for the case of curves. You could ask more general problems of degenerations in its projective varieties. And even as early as 1920s, Solomon Lefschetz had used beautiful ideas from degenerations like this to understand the so-called Hodge classes or algebraic cycles on these smooth objects, at least as a starting point of, in some sense, formal Hodge theory, by using such degeneration ideas. So the principle of vanishing cycle and understanding of cohomology of the smooth objects in terms of how they degenerate when you attach a good degeneration, a one-parameter degeneration of this kind. This goes back to work of Lefschetz. So taking a smooth object and degenerating it to a singular object and using, in some sense, principles of how the information at the singular fiber contains much information about the smooth object here is the principle of degeneration that one is looking at. So these two are two endpoints. I mean, deformations is like I'm looking at a corner object and seeing how much you can deform it. So trying to understand what happens in the neighborhood of a given object. Degeneration is the limit. I start with a good object and allow it to degenerate to a singular object. In some sense, the deformations of this object contains the smooth object. So these two principles have played a key role in lots of understanding of mathematics. I'm going to concentrate on two basic questions in this principle, in this setting here, essentially inspired by the work of Seshadri, Narasimhan, Mumford, all the giants of the second half of the 20th century. So what is the question that I'm looking at? A question which since there are lots of physicists here, I wanted to relate it to something of this kind. So this question that I'm going to look at is so what is my basic, so let V be a finite dimensional vector space over a field K, say dimension n. Okay. So what am I interested in? A simple thing that I'm interested in is, I look at, let me say, let L and K be the so-called variety or space, variety of Lie algebra structures on V. Yeah, question? Okay, so it's a very basic question. I fix a finite dimensional vector space over a field K, for example, complex numbers, and look at all possible Lie algebra structures on it. So what is this? I mean, this is can be thought of as a subset of alternating bilinear forms on the vector space V. So this is really a subset of lambda 2 of V star, the dual tensor V. So that's a vector space. As a linear space, this has got a natural affine space structure, and inside this I'm looking at objects which have a Lie bracket, which have supposed to have a skew symmetry and a Jacobi identity, a Lie algebra structure. So I'm looking at very purely, I fix some basis E1, E2, En for my vector space V, and I'm looking at a Lie bracket mu on the vector space V determined by a point, I'll simply write it asCijr, classical physics sense, as an element of K and Q, something here. So these are the Stokes structure constants, and my Lie bracket mu has the following properties on the basis. So this is summationCijr Er, R going from 1 to n. And this bracket is supposed to have two properties, skew symmetry, and 2, the Jacobi identity. And the skew symmetry will tell you something likeCijr plus Cjir is 0. And similarly, the Jacobi identity, when you unravel, will have an expression. So what one is looking at is then, now look at the automorphism group GLN, invertible matrices, is going to act on this vector space, and therefore is going to act on this, and also act on the Lie algebra structures. So we look at orbits now. So take an element G in GLN and look at a Lie algebra structure. A new Lie algebra structure can be defined as acting on the bracket operation here is going to be G acting on mu, G inverse X, G inverse Y. So this is the way in which the GLN is going to act on the Lie brackets, and we can look at the orbit of this Lie bracket, and I can take its orbit closure inside my space of all Lie algebra structures. So this space is an example of what one may be calling a degeneration of a Lie algebra structure. So this is space of degenerations of Lie algebra structures isomorphic to the one given by mu. So let me just write it as V mu as one which gives you a Lie algebra structure. So this kind of objects were studied way back in physics in 1950s by Enonu and Wigner. And they made several interesting statements about the space of such Lie algebra structures. So this is an example of a notion of degeneration of a Lie structure. One could also look at a limiting structure and ask for the deformations of the Lie algebra structure and ask what are the points which are near that. So this space of Lie algebra structures is a perfect example of where both these things come in a setting which we easily understand what we are doing here. What am I interested in, and why is my work or my work inspired by Seshadri connected with this kind of question? The following problem. I'm going to combine two issues here. Okay. So I have the space of Lie algebra structures and maybe this orbit closure, which I'm looking at, which are degenerations of a given Lie algebra structure. So what am I looking at? I'm looking at a problem now. So I fix what's called a complex linear algebraic group. Examples are GLN, SLN, and all the other groups of varying classifying types, A and B and C, and the classical Karpan-Killing classification is there. I can even assume G is what is called simply connected. So I will work with these semi-simple, simply connected algebraic groups. And the question that one is interested in is the following one. So we fix a Riemann surface and look at principal G bundles on X. Okay. So examples are vector bundles on a given Riemann surface, line bundles, as I said, that's the problem of Jacobian. All these are examples of this. This is the most general setting, and we want to classify the moduli space of principal G bundles with fixed topological types. So in the case when I'm assuming in G is simply connected, I just have to classify the moduli space here. Let me just call this moduli space as Mg. This moduli space of some natural kind was really studied by Ramanathan as a generalization of work of Seshadri and Mumford and others. So this is the most general version of this kind of moduli problem where we're looking at a general group. If you look at this problem, we are interested in two questions. When we construct this moduli space as done by Ramanathan, there's some equivalence relation and we do what is called a geometric invariant theoretic construction. So this is a moduli space which is constructed by a quotienting construction, usually written as some sort of a quote scheme or something like that, and there is an action of some group and this is constructed as a quotient. The moment you construct something as a quotient, it has good open subsets, which is usually called the stable locus, as studied by Mumford, and then there is points in the boundary where compactification is taking place, but there's a lot of collapsing, and in general you could have singularities here. In fact, for G, most of the time you'll have singularities here, and unless you work with some very special cases. So what is the problem that one is interested in? Two kind of questions which one could look at is, again, you go back to your moduli space Mg bar and take your smooth curve X that you have here, which is a Riemann surface here. So you could, as I said, you could look at boundary objects which look like nodal curves and ask, suppose I degenerate this smooth curve to the nodal curve, how does this moduli space degenerate? As I said, we are looking at, so one could even ask this question by taking even the so-called Jacobian of this X and ask how these things degenerate, and there's much work has been done. I think the final foundational work, a lot of is due to Oda and Seshadri. But the work begins with Igusa, Mumford, and several people who studied this question. And this kind of degeneration also has several applications in the theory of algebraic cycles and so on and so forth. So this is a very basic question. So I'm looking at something like, I fix a group G and look at the moduli space of G bundles on X in a certain sense and ask how this degenerates here when you go to a nodal curve. The other question that one could look at is, because this space MXG is singular, because as I said, we have used G objects and collapsed it because we are doing some large equivalence relations here, what is called semi-stable equivalence relation, S equivalence class named after Seshadri. These spaces almost invariably become singular. So you could also naturally ask, because this space is singular, is it because we constructed the moduli space in a certain fashion? Is it possible to construct smooth models for this space? So that's another question, that we have a moduli space here. The boundary objects in the given moduli space, there is a good locus, and here a lot of collapsings is taking place, so it creates singularities. Usually these singularities are what are called normal singularities in the moduli spaces, because this total space here is smooth and quotients pick up only such singularities, but these are bad enough. And one of the natural questions to ask is it possible to construct smooth compactifications of this open, nice, smooth locus, which is the stable locus? And this kind of questions also have been studied. So I'll address these two as two distinct problems for looking at deformations and degenerations. So this degeneration problem and this deformation problem both have a very interesting common platform to solve it. And this is something that I have been working on for the last 10 years, inspired by the work of Seshadri and others. So when I looked at this problem of degeneration of Lie algebras, that is, you take fixed vector space, give Lie algebra structures there and ask how they degenerate, we could ask a slightly restricted question. So my first Lie algebra that I started with here, which is the generic Lie algebra that I'm starting with, whose closures I'm taking, I could have started with something like a semi-simple Lie algebra, okay, where I want the Lie bracket to be non-degenerate and satisfying certain identities. So this Lie algebra that I start with is a semi-simple Lie algebra and ask what are the possible degenerations of that. A related question is, I can look at, instead of the Lie algebra, I could look at the algebraic group G, which is simply connected, whose Lie algebra is determined by this V comma mu, and ask, can I construct? So each time I look at this degeneration, you can see that I'm looking at a sort of one parameter degeneration. In algebraic geometry, this kind of one parameter degeneration is parameterized by the formal power series in one variable. This is what is called a complete local ring here. So I'm looking at the following principle. I'm looking at a group scheme. That means this family of Lie algebras is captured inside a big group-like picture, but now over what is called the spectrum of a complete local ring. This is like a small disk, analytic disk, and a disk in the complex analytic sense, but geometrically it will look like a curve because we're looking at complex curves. This is a complex disk, and I'm looking at a group scheme in some sense on this. The group scheme has the property that over the open subset away from the puncture here, I'm looking at the analytic disk, and away from that, I want this group scheme to be isomorphic to the given algebraic group G, which is my semi-simple, simply connected algebraic group with fixed Lie algebra. And I'm asking how this group scheme, can I construct what is called a flat degeneration of this group to define a global group scheme on the total space. How much time do I have? Excellent. So this study of such group schemes goes back to some gigantic work of what is called Brewer and Titz, and they study these group schemes on one parameter basis, and as Mumford puts it, this work is in the scale of EGA by Grothendieck, several thousand pages in period from 1967 to 1987. The work of Brewer and Titz, where they're interested in classifying such group schemes whose generic fiber is fixed and which they want to understand what sort of a degeneration is there. If the degeneration is non-reductive, can one pick up the so-called reductive part and write its root systems? And this whole study is on several of these papers, several thousand pages, and constructing these group schemes over one parameter base is a theme here. But what my observation, learning from the work of Nagaraj and Seshadri, Nagaraj, by the way, is an alumni of Faculty of Math Science, the joint work which created several new openings in this question. So we look at, in my latest work with a student from CMI, Yashonidhi Pandey, what we do, we ask a higher dimensional analog. For example, if I look at the second affine plane here and look at the regular local ring, for example, I can look at power series ring in n variables instead of one variable and look at the same kind of question. That is, if I have this on this open locus, if I know my group G, in what way can it degenerate here, what way can it degenerate here, and what way can it degenerate here? So this is a so-called point of depth 2. These two are height 1 datas like divisors. So this is like the old discrete valuation ring questions. So if I fix the data here, and if I fix the data here, can I pin down the data here? Can I construct, therefore, flat quasi-affine group schemes on the spectrum of such regular local rings? So this gives you a large class of nice smooth groups, large higher dimensional degenerations of reductive groups or simple groups. And using this ideas, I proved two things. One is that you can construct, if you take this smooth curve degenerating to a nodal curve, by looking at what I call a two-dimensional Brouhart-Titz theory, which I developed here, and then later on generalized it with Yashonidhi in the higher dimensional case, one can construct flat degenerations of the moduli space of G bundles on a parameter. So I can construct a geometric object which has all the good properties that Nagaraj and Seshadri and people like Faltings and others were looking at in the linear case. And this can be done for any G, and you can construct this so that the boundary has what is called normal crossing kind of singularities. So this new space that I'm looking at is generic fibers of the old MXGs and some nice describable objects. And here we require a two-dimensional Brouhart-Titz theory. Just a one-parameter theory is not enough. The second question that I have very recently is something connected to classical work of Narasimhan Ramanan, Seshadri, and so on and so forth. They're way back 50 years ago almost. They look at a Riemann surface X, say of genus G, and then look at the simplest case, which is SL2. Look at moduli space of vector bundles of fixed determinant in rank 2. This is, as I said, a singular variety if the genus is bigger than 2. So this they constructed a natural desingularization. So you have this open, smooth locus of stable bundles inside this, and you can construct a scheme N sitting over Mx, SL2 here, which is so-called proper and birational. That means the open subset which is smooth is not disturbed here. There is an open subset which is isomorphic to this, and this object is smooth and projective. And this was done, strangely, only for the case SL2, and for some strange reason it could never be generalized. And one of the themes that this is something that I worked on for my PhD on this modelized space of Seshadri's, and wrote a few papers as for a part of my thesis. But the obsession with this space was always there, and as to why it works only for SL2 and why not for other cases. What's the mystery behind it? So one of the things that was always behind my mind was that SL2 is essentially spin 3, or not. It is actually equal to spin 3 because of some what is called low dimensional identification of simply connected groups. So SL2 happens to be spin 3, so I always felt that what Narasimhan Ramanan, so there are two constructions here, one due to Narasimhan and Ramanan, and one due to Seshadri, almost around the same time. There is 1978, I think. And both could do it only for SL2 case. I always felt that they did it only because it was SL2 was spin 3. They were not really looking at the linear case at all. So in this, as I said, the problem is they constrain themselves to work with G bundles, but in the boundary, because G bundles become equivalence classes, they pick up singularities. So can we do away with it and ask a different kind of question? So can we allow the curve to, I fix the curve, I look at stable bundles, say stable G bundles, but now I allow my group to vary in a higher dimensional Broughart sense as a group which varies in a different parameter space, a good parameter space which has so-called versality properties. And my boundary objects, which I'm constructing from a limit in my compactification, are no longer G bundles, what I call G prime bundles, where G prime is a degeneration of G. But degeneration, not random degeneration in the Wigner sense, but a constrained degeneration in the sense of Broughart. So if I take my group G and allow it to degenerate in a constrained fashion dictated by what I call Broughart and some versality properties, you can construct smooth compactifications. So the theorem is you can generalize all these things, not for the AN types mysteriously. I can do it for the BN, DN, G2, F4, two exceptional cases to adorn my theorem. And also I can throw in C3 as the new types. Of course, this case takes up the old phenomenon of SL2. This is the odd spin and the even spin, and this has the two exceptional cases. And one can use this higher dimensional Broughart degeneration inspired by, as I said, all these developments. I always trace back most of these things to some theme or some thought that Seshadri used to stimulate by asking questions. And I just not able to get out of this, problem that he was really instrumental in laying the germ of many of these ideas or seeds. And this one can do now. This is 2023. And so these two are two large phenomena where degenerations and deformations play a role. You need deformation theory to prove that this end space that we get, in fact, is smooth, because that's a local property there. And so both these are dictated by this higher dimensional Broughart theory that I'm talking about, NBT. And one can think in the modern sense as applications of development of that theory. So thank you very much.
So we have some momentum for you.
Thank you so much.